Flavor of quarks. In the last class, we had discussed that quarks come in three colors: red, blue, and green, and their anti-quarks are having anti-red, anti-blue, and anti-green. So, in addition to color, there is another attribute for the quarks, that is the flavor. Example, the charm quark. Charm quark, it has got it is designated by the symbol C, and it has got a charge plus 2 by 3 and a charm quantum number plus 1. Other quarks are having 0 as the charm quantum number. So only the charm quark has an attribute of charm plus 1. The charm influences the likelihood of certain hadron decays. So charmed baryons and mesons that contain charmed and anti-charmed quarks have been found. Properties of ordinary matter can be explained on the basis of two leptons, that is, electron and its associated neutrino, electron neutrino, and two quarks, that is, U and D quarks. So these particles, these two leptons and these two quarks, which form the different particles, constitute the first generation of particles. In the second generation, you have the two leptons, which are uh, muon and a muon neutrino. Then the two quarks associated are the charm and strangeness quark. These are responsible for the unstable particles. These are also responsible for the resonances in high energy collisions. Next, you come to the third generation of particles, which are constituted by tau particles and the tau neutrino. These are the leptons associated, and the quarks associated are the top quark and bottom quark. So red, blue, green plus charm. Then you have this top and bottom. So these are the different varieties of quarks. The quark confinement. We have not been able to isolate quarks. Even though we have identified different types of quarks, isolation of quarks has not so far been possible. Quarks are supposed to be connected to each other, just like connected by a spring. If they are close together, their interaction is less. If we try to move them apart from their normal spacing, their attractive force increases as if connected by a spring. When enough energy is added to the quark, they don't break free or they don't become free quarks. But the excess energy is used to produce a quark-anti-quark pair. This results in the escape of a meson. Mesons consist of quark and anti-quark. Let us see a neutron which interacts with a gamma ray photon. It gains energy. That excess of energy creates a quark-anti-quark pair over here. UDD is the core composition of the neutron, plus the energy gets converted into a quark anti-quark pair, and what happens is this will finally result in a proton DUU plus a pi minus meson, which consists of U minus D. So this is what happens when excess energy is taken up by the quarks. Now the charm top and bottom quarks, they are designated by the symbol C, T and B, and they have the charge plus 2 by 3, plus 2 by 3. Bottom quark has got a charge minus 1 by 3. The strangeness is 0 for all these because the strangeness is 1 only for the strange quark, and the baryon number is 1 by 3, 1 by 3, 1 by 3 for each of these. Quarks and leptons and the interactions affecting them. Ordinary matter, only the first generation quarks are involved. Each quark and lepton has an anti-quark and anti-lepton. Let us see this. Let us look at this table. First generation consists of U, D quark, and electron and its associated neutrino, that is the electron neutrino. Second generation, charm, strange, muon, muon neutrino. Third generation, top, bottom, tau, and tau neutrino. So these are the leptons and the quarks involved. Now, let us look at the charge. Color is also attributed as a charge only. So the electric charge of these UCT, that is up, charm and top quark, has got electric charge plus 2 by 3. Then down, strange and bottom quark has got electric charge minus 1 by 3. And the color, each of these come in red, blue, red, green and blue colors. While you look at the leptons, that is electron, muon, tauon, and their associated um, neutrino are colorless particles. Neutrino is electric charge 0, electron, muon and tau particle has got electric charge minus 1. Now the interactions associated with each of these. Color is attributed only to the quarks. So this region is the quarks for which the interaction color is there. Then electromagnetic interaction. Other than the neutrino, which is chargeless, all other particles are, these particles are charged particles, so they come under the electromagnetic interaction. Now the weak interaction, all these particles undergo weak interaction. Next we come to the field bosons. Which are the bosons which taking part or the carriers of each of these interactions? Electromagnetic interaction, you have the photons. Gravitational interaction, you have the graviton, which has spin 2, and gravitational waves have recently been detected using the LIGO experiment, so we can expect the graviton to be detected. Then the weak interaction consists of intermediate vector bosons, which consists of W boson, which has spin 1 and charge plus or minus E. Then it takes part, the result of this interaction is ordinary beta decay. Then you have the Z bosons, which has got spin 1 and charge 0, which is involved in the high energy events. Then strong interactions, that is interaction between quarks. The intermediate particle is gluon, which is being exchanged between these quarks. They are massless, they have the speed of light, and it has a color and anticolor. A gluon is associated with a color and an anticolor together. So emission and absorption of a gluon by a quark changes its color. If a blue quark emits a blue anti-red gluon, then this particular blue quark will become a red quark.